Science on Surfaces.
Hello there and welcome to this podcast, Science on Surfaces, Tips, Tricks and Tools with me, Malin Edvardsson. So today we will talk about QCMD technology. We will talk about what it is, a bit about how it works, when and how it's used, and some pros and cons. So here with me in this call I have two of my colleagues, Erik Nilebäck and Fredrik Pettersson, both senior application scientists here at Biolin Scientific. Welcome.
Thank you.
Thank you.
So Erik, your background is in surface science, biosensing and project management.
Yes.
You have a Master of Science in Engineering, Biology and Devices and Materials in Medicine from Linköping University and a Ph.D. in Bioscience from Chalmers University of Technology.
Yes.
And your Ph.D. project was on developing new biosensing application areas for QCMD.
Yes.
And you've been working at Biolin Scientific for 8 years?
Yep.
Yeah. And Fredrik, you have a Master of Science in Biophysical Engineering, also from Linköping. And you've been working with application and technology development for analytical instruments since even before your master's graduation. And you worked with multivariate gas sensing at Nordic Sensor Technologies and cell-based assays and electrophysiology at Selectricon. And now you've been working with QCMs, QCMD at Biolin Scientific for about 9 years. So these are great backgrounds for today's discussion on this technology. So let's just dive in and start with the basics. I mean, QCMD. How would you describe this technology to someone who's never used it and who's not familiar with it? Fredrik, you go.
Yeah. To start with, it depends a little bit on the background of the person. If you come from bio background, biochemistry or biology, you would, for one thing, say that it's label free, that it measures molecular interactions and molecule surface interactions without any labeling. If you come from other areas, maybe it's more appropriate to say that it is a mass sensor measuring mass bound to a surface, a specific surface, and that we also can measure properties of the material bound or the binding, like soft or hard.
Yeah, so surface sensitive, time resolved method.
Yeah, time resolved, I forgot, but yes, that's true. You can, of course, that's one of the great advantages of QCMD, that you can follow the entire process and with quite detailed time resolution too.
Yeah.
Mm-hmm. So, please go.
Yeah, sorry, I would say that's also similar tracks I usually use to describe it, and depending on the level of the person, I mean, technical level of the person you're talking to, it could also be just a device to weigh molecules, more or less. I mean, if you really want to be more kind of fundamental in your description. So, exactly, both mass and structure I usually add in.
Exactly, and we actually didn't mention the abbreviation QCMD is short for Quartz Crystal microbalance with the dissipation monitoring. So it is a balance for small masses. So what, how would you say, like what mass resolution are we talking about in terms of what we can measure?
I mean, it's in the nanogram range, yeah. So molecular layers, single molecular layers, and larger structures on top of that, up to a few microns, I would say.
So monolayers, I mean, that means that we can really measure the single, fairly small molecules also, and single layers of those. So it's pretty much as small as you can get without going sub-atom size.
Mm. And if you would compare it to similar technologies where you characterize surfaces or molecule surface interactions or layers at surfaces, how would you compare QCMD to, for example? I don't know, AFM, ellipsometry, SPR.
Do you want to start,
Maybe you
Fredrik?
have more experience about that, Erik. I mean,
Yeah.
for one thing, we actually measure a mass. So you use a sound wave to probe, and that's quite different from most of those methods, for instance, SPR and the ellipsometry and the optical methods, because they don't measure the mass, they measure a change in refraction index.
Yeah,
So
exactly.
this would be a more direct measurement. AFM I haven't used at all, Erik. Have you any
No.
comments?
Yeah, so I mean, I basically during my PhD I used those techniques and QCMD for the surface chemical systems that we studied, like hydrated polymer layers and biomolecules. And I would say, as you say, Fredrik, you actually using a scale in QCMD with acoustic sensing, and then you can complement that with optical techniques, so you can get complementary data about the mass, for example. So the optical techniques do not measure the coupled solvent. It's usually water then, in biomolecules. But then and there are so the structure. I guess you mentioned that, Fredrik. Short memory, but I mean, you not measure the structure rearrangement in the optical techniques. Usually, you can see it as a change in the refractive index, but it's hard to quantify.
So both of you have mentioned acoustic technology. So what is an acoustic technology?
Yeah, so I mean, actually, you're measuring vibrations. You're not measuring. So you're actually measuring the waves that propagates into the movement of the crystal more than changes in, for example, light. So you can compare the vibrations of the crystal to the vibrations of a guitar string or something similar. So you're actually measuring those kind of frequency changes.
Yeah, so let's talk a bit more about the working principles. I know, Fredrik, you've talked a lot about and explained a lot, or you often explain how this technology works. So maybe you have a straightforward way to describe to the listeners.
Yes, so that was my reaction when I started as an application scientist here, that I thought we had quite complex and very much mathematics in our explanations about the fundamentals of QCMD. So I started thinking a lot about it and figured out, yes, it is an acoustic method, a vibration being transmitted through a layer and a liquid. It is a sound wave. So sound waves are what we are measuring and what we are interacting with the QCMD sensor. So in that way, you can say that the quartz crystal itself, it gives a tone. It's our QCM sensors have 5 megahertz as a fundamental frequency, their basic tone. So of course it's ultrasound and very, very high ultrasound. And in difference to kind of the medical ultrasonic measurements you're used to, we're not measuring time to the reflection, but you're actually measuring how a layer on top of the quartz sensor itself affects the sound, the tone level. If you have thicker layer, you'll get a lower tone, just like a longer guitar string would give a lower tone. So there we measure frequency change that's actually directly related to mass. And then also if you measure how the sensor gets dampened, how the oscillation dampens out and dies out after you stop stimulating it, that gives you the material properties. But all in all, has really to do with how sound waves propagate through the film you're measuring and out into the liquid around it.
So we measured 2 parameters. One is the sound and how the sound changes when
Frequency, the tone, yes.
Yeah, the frequency and the tone. Yes, exactly. When molecules absorb or bind to the surface. And then we also measure the decay time of the tone. And that says something about the softness or the structure of what's on the surface.
Yeah, or I mean, or if you, in other words, how much energy that is lost during each oscillation of the crystal. So when the crystal moves, how much is dampened.
So we get information on mass changes and also structure and structural changes with QCMD.
Yes, so it's just like, I mean, take a tuning fork. If you strike it to something and it will ring for a very long time when you hold it up in air. But if you kind of wrap the tuning fork in a blanket or something soft, then the tone will die out quickly. So there we can see the dissipation measures how soft the layer around on the sensor or the liquid surrounding it is.
It's very straightforward to imagine that it would be more difficult for the tuning fork or whatever that oscillates. It's harder to move when you put something heavy on top. So the heavier the whatever you put on top, the harder it is to move. Which then,
Yes, exactly.
Yeah,
Not really harder. I mean, that's a bit of a misconception. A high mass load won't really hinder the sensor for vibrating. It will just vibrate slower. So you don't really get affected in the amount the crystal vibrates by the mass itself. So a thick layer is not a problem. What gives dissipation and this dampening material effect is when it's soft, because then you will actually have this interaction that the vibration dies out more quickly, and that's how you kind of measure the softness.
Great. So, I mean, both of you have experience using the technology. So, I mean, how have you used it? Erik, you started already during your PhD.
Yeah, or even before that. I
Or even
actually
before
started
that.
during my master thesis. So, yeah, both my master thesis and then in after that, or following up that, actually, my PhD project was a collaboration between the Biolin Scientific and Chalmers University of Technology, industrial PhD students. I used QCMD as my main technique, and then complementary techniques to kind of study our system. So I used it for all kinds of biomolecular systems. So going from mainly using biotinulated systems, so that is a coupling chemistry to be able to have very specific binding of biomolecules on a surface. So we have, in our product portfolio, we have a biotin sensor. That was part of my project to develop that and then to use that on different types of systems. So that was both biotinulated antibodies, biotinulated kind of carbohydrate layers, and then also looking at kind of repeated antibody-antigen interactions. Also to the carbohydrate layers, we also looked at cellular interaction, so they we combined it with light microscopy to study that as well. So during that time, it was a lot of focus on biomolecular systems and then kind of the bio side of QCMD.
So what questions were you asking that the QCMD could help you answer?
Yeah, so there was a few, but mainly kind of working with specificity. So they could measure specific interactions. So we looked at both specific conformational changes in proteins, and there we could actually measure these conformational changes and verify that with the dissipation shifts. So they got elongated when they changed conformation, and then we could see that as a dissipation signal, and that was specifically triggered with known drug molecules. So it was a novel way of looking at conformational changes for that system. And then a similar way in the carbohydrate systems, we could use enzymes that we know degraded these systems and see the specificity and compare that between different systems. So quite a lot of verifying the biological activity of the layers on top of the QCM sensor. Like I say, it was a lot of the focus of our PhD work. So kind of developing new strategies or protocols for using the techniques.
And what would you say, Fredrik, are questions that are asked? What other kinds of questions have you seen be asked?
I mean, to start with, my first experiences of QCM, Quartz Crystal microbalance, has been with thin film deposition, when you have the vacuum systems and you sputter or thermally evaporate metals on top of silicon wafers. And for that purpose, we use the QCM calibrated basically just for the density of the metal, and then you can get the deposition speed readout quite easily. But I mean, compared to these instruments, compared to QCMs, are very crude. I mean, they have low resolution, and you don't really mind so much about the linearity. And of course, you measure nanometer size there of a very rigid layer. So as an analytical technique, of course, the sensitivity is higher. And when I started here at Biolin, I started working with development of the instruments, and we were on the brink then to launch our automated instrument, QCMs Pro. And there we had to work a lot with details and reproducibility and things like how does the instrument hold the sensor, how can we increase the reproducibility in sensor clamping, sensor holding in the instrument, how can we make a flow cell that fills reproducibly by a robot every time without an air bubble formation, and also how can we keep temperature control stable enough when there's a robot coming in and pipetting liquid basically not onto but very close to the sensor. So there's a lot of questions there you really needed to work on to be able to take advantage of the precision and the kind of extreme resolution in the QCMD method. So that has kind of been my way into the company, and also kind of my bridge over to application development, where I'm working now to work with those issues. How can we prove, how can we improve, and how can we prove their reproducibility? So I've been working with some demo experiments that we see the fruit out now. One important issue there is when you get out doing a demo to a customer, can you have a clean enough sensor? Working in someone else's lab, then you need to clean your sensors to make a good demo, but that might be difficult and very stressful in someone else's lab when you don't know exact equipment they have, etc. So so that has been very close to my heart, kind of see where the limits is in reproducibility. Can we see that a certain protein always binds a certain amount? So I've been working a lot with albumin as a model protein, which is very predictable. We know the size of it. We can anticipate what the monolayer of albumin, how large signal that would give. And also, how can you work with coatings on a sensor to actually reduce variation from the cleaning of the sensor, etc. And also a little bit in how can we really, at the demo, highlight this quality of the QCMD data, that you see change in the material properties together with the mass change. So, I mean, trypsination is a pretty cool experiment to do in the QCMD sensor, because you really see how the layer softens up and that you get fragments kind of slightly going out into the bulk solution and kind of waving around, increasing the dissipation, and then you start loosening the mass. Yeah. So that is really interesting phenomenon to study with QCMD, because you see so much things happening. I mean, having an albumin on the surface and you bind in the trypsin, you see a little bit shift when the trypsin binds in, but then quite rapidly it starts cutting, the protein change, and you get the increase in dissipation, and then after that comes the mass change. So there's so much information in this, just seeing the picture here when you change one protein to another, and you see different phases of this, and the time resolution is really so quick, so we can see the trypsin binding, and then you can see it start cutting. So that's it's quite, yeah, it's fascinating. It gives you so much detail on what happens on the surface.
Mm.
Yes,
Yeah.
I agree. Yeah.
So we have you've mentioned a few examples now, but how would you guide someone in general to when this technology could be used or could be helpful to use?
I mean, I would say in general, when you're interested in looking at the molecular scale, and you, especially if you're talking about interactions. So if you have a material that you know interacts with another material, you want to know how that happens. So want to actually look at, especially if you want to look at how and when it happens, so time resolve in more details. And and if you know that it's kind of a soft or could have viscoelastic properties, as we call that with another name commonly, I would say it's a real jackpot, because then you can really see things. So, and especially if you, for example, you will be interested in, I don't know, metals or polymers, or or it would be biomolecules, I would say that you're very close, or polymer layers. But it could also be, if you're interested in seeing how bulk materials interact with a surface, for example, you can also have these effects, even that can be. It's another type of measurement, but there's, I don't know. For me, the possibilities are are endless, more or less, when you're actually interested in the details, and you need to be interested in what happens at the molecular level. So I would say then it's a very good technique to use in different circumstances.
Yes. Yeah, I agree with you there. I mean, you take the biomolecular perspective quite a lot there, and I would say out of that, or even within that scope also, if you look at things like protein aggregation, for instance, one of the advantages is that you can follow, you have resolution enough to follow the single molecule interactions with the surface, but then we can really work to 1 or 10,000 times thicker layers. You can go up all the way to micrometers. And that's pretty outstanding that you can follow this length really from aggregation onset. You can see the first monolayer of interaction with the protein. Then you can follow the dimerization and the multi-layer formation and eventually the aggregation process that eventually also leads to some structural change in the protein itself when you go to really thick layers. So that range with that precision, that's pretty unique here, that you can follow the entire scale of aggregation processes and the fouling processes also. So that's an advantage in many applications. And of course, in difference of many other surface-sensitive techniques, it's that we actually study the exact material surface. So the only method I know that really measures the same thing is the very simple method, contact angle, where you actually measure the first interaction layer, but then contact angle, that method gets messed up when you have adsorption phenomenon going on. So that's more after and before, and you don't get the exact weight, but you get the change of the surface property. But QCMs also measures that kind of interaction between the liquid, the surface, and the solute being solved in the liquid there. So you can really study all that kind of three-part system of your molecule, your surface, and your solvent. And with a huge range of different materials, and that's also pretty unique that you can do that.
I would second that you're very free in the type of materials used in your sense. So that is something that is really that kind of drives the applicability of QCMD in many ways.
Yes, definitely, and that of course means you can study really detailed phenomena. You can study even different formulation of a polymer like nylon or something. You can actually look at one formulation with some softener added to the nylon, or another one with longer or shorter chains of the polymer, and you can see details in how they get swelled by a solvent, maybe how the polymer gets removed by a solvent, or how something absorbs to it. So you can really see those differences in the actual material on the level of differentiating different formulations of a polymer. So in that sense, it's a very realistic method. You work with a real surface, with advantages and disadvantages, of course. So when you look at that level, contamination, you see differences there a lot. Your cleaning affects it. So
Fredrik, you mentioned briefly before the like the standard or the classical QCM, the plain QCM. So if you would compare QCMD to other QCMs, how would you compare it? Because there are lots of other QCMs out there, also in addition to the standard one. QCMI, QCMR, QCMA?
Yeah, it depends on the measurement method. So all are based on the quartz crystal and the piezoelectric properties of the quartz that itself kind of translates a vibration, an acoustic vibration, into an electrical signal. So that's what all of these instruments are using. And then the main difference is in what electronics you use to record that vibration or the changes. The most simplistic one it's called a resonance circuit. So that actually uses electrical circuits that puts the crystal and the electrical circuit together in self-oscillation. And that means they will kind of track change in the resonance frequency only by measuring either an output voltage from that circuit. And they have, for one thing, that's a very simple circuit, quite cheap, and you can get the voltage out of it, so very easy to sample in a computer. But they cannot be too fast, because then they will kind of get unstable if you try to probe that resonance kind of higher. And then since the output voltage is proportional to the mass to it, you get some limitations in things like the ADC measuring that voltage, etc. So they have a kind of larger steps in the resolution of the mass bound to the sensor. So good enough for cheap applications. And then you have the intermediate there, and that is using kind of these circuit analyzers. So that is an electronic piece that can apply a frequency, so voltage sinus wave at different frequencies. And while it does that, it can measure the amplitude of the current going through the quartz sensor and also the phase shift. And the phase shift is kind of related to capacitive properties of the sensor and surface bound material and the entire system. But then you can sweep this and really measure like frequency scanning or impedance spectroscopical like, and measure the peak of the resonance, and you can see the width of the peak, and that means you can get information on the dissipation of the system. Those can kind of basically approach the sensitivity of QCMD, but they are much slower since you need to scan many frequencies. But the advantage also, they are based on a kind of standard piece of electronics. You can buy one of those impedance analysis instruments, circuits analyzers. So they will become a little bit cheaper. And then you have the QCMs, where we measure with a ring down method, where we stimulate at the latest known frequency, and then we measure the entire decay curve. So that means for every time we stimulate the sensor with QCMs, we get one frequency and one dissipation value. So that makes this a much, much faster. And also then, of course, since if you don't need to measure fast, it means you get more data points to average to reduce the noise.
So the first category you mentioned measures one parameter, a single frequency. And the second category measures frequency and bandwidth or impedance or dissipation, some sort of energy loss.
Yes.
And then QCMD also measures two parameters, or the QCMD measures two parameters. And you also have the multiple harmonics. Yes.
Erik, do you want to elaborate on those? I mean, the resonance cannot measure harmonics at all. Then with impedance spectroscopy, you can do it with the circuit analyzers. You can do it, but the higher range there, the more expensive that part will be. And of course, QCMs can do that by default, measure different harmonics. But the advantage of that, we want to elaborate, Erik.
Right, we have several harmonics.
Yes.
I mean, it's basically for the identical system, you get a larger set of data. So you can enable modeling of applying different kinds of physical models based on theory. So for viscoelastic properties of the layer, so both storage and loss modulus of your layers, and then also thickness, mass values, not being restricted to for rigid layers. You have a more of a linear relation through the well-known Sauer-Bray equation. Basically, have a constant times the frequency. You get the mass estimated mass value, but you can use with viscoelastic models. You can use with soft layers. You can get also additional information, and by having the largest set of data from the overtones or harmonics, you will be able to model, because you need input data to be able to have a high quality modeling.
Yes. So I mean, you use the property of sound and how the different frequencies, when you go to from 5 to 15, 25,
exactly.
35 megahertz, and how those sound waves actually behave a little bit differently.
Yes.
Depending on the layer properties.
You can actually find information within the overtones or the harmonics as well. So they have a little bit different. So the higher overtones propagate a little bit shorter into the sample, for example, and then for thick layers, for example, when I studied cells attaching to the sensors, we typically looked at the fundamental or the third harmonic, because they propagate longer into the system. Yep. So you can also have those advantages. You can actually discriminate things happening on the sensor between the harmonics. But I mean, I would say the major advantage is that enable modeling and using that. But then also you can get this added info just because they behave differently.
Yep. Yeah. But also, I mean, from the user perspective, one really important aspect is that if you look at the fundamental only, we know for sure that the fundamental frequency is definitely a lot more sensitive to all kinds of disturbances. Yes. And that's, I mean, QCMD is a very sensitive technique. So of course it's sensitive to all kinds of stuff that you don't want to measure, and that you need to keep down. So the fundamental frequency is more sensitive to mechanical stress. It senses all over the sensor surface, which makes it more sensitive to variations in the clamping, how the sensor is held. It is kind of, since it penetrates deeper into liquid, it's more sensitive to air bubbles flowing through the flow cell. And temperature sensitivity is kind of the same for all of the harmonics, but it's much easier to keep things in check if you use the higher harmonics and not the fundamental, because the fundamental one is very sensitive to disturbances. Yes. And my recommendation for any user is to always record the fundamental, because that's a good quality indicator. Yeah, and then if you can actually use that signal for your measurement, then you're lucky.
Yeah.
it happens. It happens. Yes, if you keep good control of your experiment, you can do it. Yeah. But usually just keep it as a quality profile and see. Okay, I've got some strange noise in the F3 now, and then you can see F1 had a big jump in it or some disturbance from an air bubble or something. Okay, then you know. Okay. This was not a measurement signal, this was just some disturbance.
Yeah, exactly. You should always record the fundamental. It's good to use.
So now we've touched upon pros and cons, and you're describing this high sensitivity both as a pro and a con, actually. Right? Yes. Because, I mean, high sensitivity is great, but it also makes it a bit more tricky maybe to handle or to run measurements reproducibly.
Yes, it might, and one thing that it's important, but that is for all surface sensitive techniques that are sensitive in their signal. You need to have a reproducible way of preparing your sensors. You need to know that you have clean sensors and that you have clean solutions, clean tweezers. I mean, everything. The process needs to be controlled. So, but that goes for all techniques, I would say, that are similar. But it applies also to QCMD. So it is a sensitive technique, and you can really measure details of the layer interactions and what happens at the molecular level. But that also means that you need to have the cleanliness at the molecular level in check. So
because it will also measure dirt if you have dirt present.
Yeah, exactly. Yeah. And of course, this might vary from system to system how thorough you need to be. I mean, if you measure interaction with thick layers, so you have a lot of, for example, real big aggregates being formed, or you're measuring complex fluids, then of course it might be a little bit different. But I mean, I'm a little bit biased coming from the surface chemical side, where you are very picky about these things, preparing your solutions, looking at single molecular interactions. But I think in ways it's something that can be an advantage when you have everything in place and you know what you're doing, you know what you're looking at, and you can be kind of confident in that you have actually looking at what you hypothesize that you're going to look at. So, but it might be a drawback that it can be time consuming sometimes with sample preparation.
So could you just, briefly describe an experiment? I mean, to someone who's never used the instrument, how would you actually run an experiment or a measurement with this?
Yes, I mean, to start with, of course, you need to go down into the lab with some kind of plan what you want to do. But the first thing I do, that's always prepare my sensor. So clean it to the level of cleanliness I need. And of course, that depends a little bit on how thick layers I want to measure. And also, I mean, how lifelike surface do I need? Am I a surface scientist? Then I maybe need a molecularly clean gold surface or silica surface just to be sure that I can bind my next layers in a perfect way. But if you're interested in a more realistic situation, then you might actually want to have a slightly contaminated stainless steel surface that corresponds more to a lifelike situation.
Yes.
But anyway, either of those approaches, of course, you must make sure that your pre-cleaning protocol ensures the reproducibility so that you have the same surface every time you repeat the instrument, and also that you get low drift. So, for instance, if you have some contamination of the surface, it would be a bit tricky to get to a good stable baseline if you if you start cleaning it out by the experiment buffer you're using. So that's first thing, clean the sensor in a reproducible way, and then really mount the sensor in the instrument and set the instrument to your correct temperature.
Which is very important.
Yes, it's super important, and that's the most common reason for drift in QCMs measurements is that you haven't stabilized the temperature for long enough. I can also recommend that sometimes it can be quite good to do some of the cleaning inside the system also. If you want to have really, really good stability, it can be quite good to actually do the cleaning in the flow cell in the instrument, because flowing the sample in a low height flow cell can actually speed up chemical processes like cleaning.
Yes.
So next step after that, then I would go out to the lab and prepare my liquid samples for the experiment, if it's a protein or a surfactant or whatever samples there are, because why not take advantage of this time? I want my sensor to get stable at the measurement temperature. When preparing the sample, I will be very careful with contamination risks. And I mean, if a contaminant has higher surface affinity than the molecule you think you're measuring, then you actually might ruin your experiment completely or draw your own conclusions. So it's quite good to be aware of the quality and the purity of your molecules you're using. Again, here, that might be something you want to reproduce. If you want to look into a mining process and they use industrial quality surfactants, then of course you should use the industry quality surfactants, maybe 75 or 80% purity, but maybe then also compare them to real pure analytical 99.5% pure molecule. Of course, let things take time. Surface active molecules usually have tendencies to also aggregate. So be careful with solving your molecules. Use ultrasonication, for instance, to get rid of both air in the liquid, and also make sure you break apart any aggregates. So what's next after that, Erik? Did I forget anything?
Yeah, so you have your molecules dissolved in the buffer that you're going to intend to use, and then so you have both kind of background buffer, and you have your samples diluted in the concentrations that you're going to use. So, and then after that, so you have stabilized your sensor in this instrument and the temperature, and then you add background buffer and stabilizing that, and then you add your analyte. And be sure, I prefer to use, for all my experiments with QCMs instruments, I prefer to use the notes within the software, always. I mean, if you use the Pro, you're gonna get it automatically from the samples you have noted that you're gonna use and the times, etc. But for the Analyze and Explore systems, I encourage people to use the notes because it's really good way of keeping track of what you do.
Yeah.
And adding times, etc. Because it's not that easy always to remember exactly what you did. So that's a good idea to do. And then, I mean, if you were talking about the simplest biomolecular adsorption, that would be buffer, adding your analyte, and then rinsing with the buffer again. Once you have, I know this is something that Fredrik likes to talk about, that you have stabilized your signal. So you have a kind of saturation in the signal, so you don't see the drift. Hopefully it will be flat, so you have really come to equilibration state.
So this can take 5 minutes or 3 hours or even longer.
Yes.
Yeah, I mean, that's super. I've seen so many measurements, even from publication in renowned journals. We have seen that they claim, we are approaching equilibrium, and then they stop the measurement. And maybe even just stop it and don't measure the desorption phase and how stable the surface was in buffer. So that's, I mean, always start and end in the same liquid situation. That's crucial.
Yes.
And also baseline, make sure you take some minutes, 5-10 minutes of baseline to be sure that you really have low drift compared to the size of your signal. So if you're measuring for 1 hour and you're measuring 50 or 100 hertz of signal, then you wouldn't need to care so much if you have 1 hertz per hour drift. But if you're measuring 5 hertz signal, like a really thin amino acid layer, then of course 1 hertz per hour is kind of borderline, and you need to see if you can improve it a little further, which you can. So that's quite important. Setting your pump to the right flow speed is important also. I mean, the standard flow module for the Analyzer and the Explorer is about 40 microliters. So that means having 100 microliters per minute would have complete liquid exchange in the flow cell in about 1 minute. And the same for the Pro system, where it's only 17 microliter, then 30 or 40 microliters per minute would give complete liquid exchange in 1 minute. So compare that to your experiment length, because of course if you run higher flow speeds, you will have faster liquid exchange and more sharp onsets of your kinetics. But on the other hand, if you run really long experiments, you would consume a lot of liquid. So that's it. So that's one thing that's important to keep control. And then of course this run to equilibrium and be sure it is equilibrium. If you're studying protein adsorption, for instance, you will get often a very quick signal from the first layer, monolayer proteins absorbing. But then if you actually have some conformation change in the protein, that will start promoting aggregation. That can take time and means that you will have a much, much slower kinetics in the following stages of aggregation and the following multilayers. So that means you cannot really only approach a plateau. You need to be sure, is this really a plateau, or do you have some aggregation tendencies that... So even if in a protein adsorption, the first monolayer maybe takes 10 minutes, and I will run for 2 hours just to be, if I'm interested in the multilayer formation, that can have very different kinetics.
Exactly. I mean, you can see a whole new phases in adsorption being formed. So it can be very interesting data being hidden.
And why is it important then to end with the buffer, the same buffer as you started with, or the solution that you talked about?
So you need to be able to compare. So you need to have basically you need to have the same viscosity and density in the background buffer if you want to model your data. That would be the short answer. Or do you have What would you say, Fredrik?
Yeah, that's one thing, because I mean, QCMs being very sensitive, we also measure, of course, differences in the liquid itself. If that one has different density or viscosity, we'll actually see a little bit change of signal. Usually not that much problem if you are below, say, 1 milligram per milliliter.
Yeah, that's true. That's true.
If you're at that scale, you will usually not have much viscosity shift. But if you go higher than those concentrations, you would actually need to measure or verify your viscosity of your sample liquid, because that one might be different from the buffer itself. And that's of course good to know when you model your data, and the only way to be sure that you're actually at the exact same situation afterwards, going back to the same buffer. But then also off kinetics is quite interesting to see how does my sample release from the surface. Will that tell me anything about the interactions?
Yeah.
And of course it does. So it's always good to do that.
Mm. Okay, so we talked about a lot of situations where QCMD technology is very useful. So what are the limitations, or are there any situations where you wouldn't recommend using it?
I mean, we touched upon it now, but that is if you're going to use very viscous liquids. I mean, very highly viscous, because that will dampen the signal, so you can't actually measure it. But then we're talking about very, very high viscosities. I don't know these numbers by heart, but perhaps you know that, Fredrik. The viscosity.
You start losing the highest harmonics really around 10 to 15 centipoise.
Yeah.
And then I think you can measure around 50, 60 centipoise at max.
Yeah.
So that's about where it goes. Of course, you can increase the temperature to reduce the viscosity and measure even at viscous solvents in low temperature. But that's a real limitation. I don't think the situation is so much better with other surface methods like SPR, the optical ones.
They will, of course. So there might be no other techniques that can be used.
So maybe it's an advantage.
Yeah.
Yes. One thing I could mention is, I mean, if your surface isn't stable in the buffer you want to measure, that might be a limitation. But I know customers using that situation. So they see something washing water, they see they take off a few nanometers per hour or some angstrom per minute. And then they see if I add this surfactant or if I change the pH in this way, then you will have a difference. So of course you can do a slope analysis and look at desorption rate or cleaning rates or adsorption rates in different situations, even if you can't get a stable baseline. But it would be very difficult to kind of measure absolute thicknesses there. But you could still measure differences in desorption or adsorption speeds.
So talking about surfaces, then what real-life surfaces can be used? Are there any limitations? Of course there are, but how would you describe those?
But I mean, if we talk about this is a real advantage with QCMD, as we have told before. But since you're not, if you compare directly with an optical technique like SPR, for example, then you need to have a surface plasmonic active surface, or if it's ellipsometer, you need to have a reflective surface. And I mean, you're not limited to those kind of restrictions. Of course, you need to be able to coat it on top of the sensor, and it needs to be stable, as you say, Fredrik, in the solvent that you're gonna analyze it. But you mean you can use metals, polymers, oxides in different ways, as long as you can coat them on a sensor surface. Yes.
Yeah. Yes. Really, anything. It of course must bind tightly to the surface, but
exactly.
Polymer ceramics, nitrides, and as we mentioned earlier, you can actually look at real formulations. We can see difference between soda lime glass and borosilicate glass, and different steel formulations, different steel types, different types of stainless steel, for instance. So that's possible to do. One restriction is homogeneity.
Yes.
It's a big advantage having a homogeneous layer. You can measure porous layers, but it's a lot more difficult to analyze the data in that case. And of course, small differences in pore sizes might change your measurement situation a lot in that case. So that might make things a little bit messy. And of course, the top layer on top of the quartz sensor. So the quartz sensor is actually built up by a single crystalline slab of quartz. The thickness of it is what defines the fundamental frequency, the resonance frequency. So our sensors are 0.3 millimeters thick, about. So that's pure quartz. To be able to stimulate that electrically and read the signal, we actually have a gold layer on top of it. But gold doesn't stick very well to quartz, so in between it's an adhesion layer of chromium, or at some occasions titanium. So quartz, then it's chromium, gold, and then on top of that you need to put your sensor material. And but you can really use any technique there. You can use sputtering or spin coating or some kind of inline flow method, just by dipping in something. So very flexible there. But what we can't do is put thick things on there. You can't put like a piece of fabric or
like a real roll paint, for example. It's not really possible when you get almost millimeter thick films. I mean, very thick films. That's not possible.
And I guess not even those kind of 20 micrometer thick polymer films. I don't think we can use it either.
No, like taping films of that kind is also then you're getting too thick. So you need to have a thinner model system for those.
So when you say thin, I mean, what thicknesses are you talking about?
I mean, it depends a little bit on how well it sticks to the surface.
Yeah.
But I mean, if it's a soft layer, you can't have as thick as you would if it's a rigid layer. So that depends. But then micrometers.
But on the other hand, if you look at the interaction with such a surface, if you're interested in a material that is actually 20 microns thick or something, is that really the same thing as surface interaction? How would you characterize if you have 20 micrometers thick layer? Then maybe you have inhomogeneities in the micrometer scale. So how relevant is it study nanoscience on that kind of surface? And that's very relevant. I mean, you need to have the right model system, and surface science on the nanometer and angstrom size. That is it goes crosswise our intuition sometimes.
Yeah.
And we have sometimes questions about cotton fibers for detergent measurements and how can we get cotton onto the surface.
Yes.
And then you're really thinking the wrong way, because a cotton fiber is 10 to 20 micrometers wide. So just having that on the surface will be over the thickness limit of the QCMD technique. But then the fiber itself, you don't really interact with the fiber. Yes, you can absorb into it, but the fiber is built up of thin layers of kind of well-structured cellulose fibrils. And those are kind of the scale. So if you take cellulose, as in the fibrils, and you put them down on the sensor, then you can get a flat layer. And then you might maybe add some fatty acids or some proteins, other proteins as in a real cotton fiber or realistic textile fiber or wood. So it is those things that give the difference between the different types of textile fibers or wood fibers. But that is really the scale where we look with QCMD. If you interact with the monolayers or multi-layers of cellulose microfibrils. So that would be kind of taking a cotton fiber, take the top layer of that one, flatten it out and put it down on a sensor. And that's also the relevant scale for the molecule interactions with the cellulose. So it makes sense not only from kind of what the restrictions is with the technique, but also from the kind of interaction perspective. That is the model scale you need to be on.
Yeah, because I mean, what you would, if it would be possible, now it's not might not be technically possible, but if you would coat with cotton fibers, what you would actually look at is the interface between the cotton fibers and the sensor. That is the sensing area mainly for the QCM. So you would look at these surface interactions mainly in any case. But if you have a model system that is tailored to work well with QCMD, then you will get a much better and more reproducible signal.
Yeah, or even if you could make the cotton fibers attach really tight to a sensor surface so they would vibrate with it, then you would measure the liquid between the fibers. So
yes, totally
so
different. Yeah, exactly.
So it's
So is there any other key information related to this technology that we didn't cover so far that you would like to add?
I would say what I have like a reflection I made when I started using QCMD a long time ago, that it was, even though it might sound that there's a lot of things to think about with cleaning, etc., but it's kind of straightforward how to use it. Then you start to get your data, say, okay, frequency decrease, mass, something is bound to the sensor, and you really don't need more info than that to be able to start analyzing, start doing measurements. So it's quick to get up and running with the technique. Then to get into the finer details, like all techniques, you need to time and to get into that. But then to start doing measurements, that's quite straightforward, and that is a real advantage. You can try new things. You can use it as a workhorse technique to really try different systems. So that I think is something to keep in.
Yeah, I agree. I mean, it is a good technique since you can do the application development on the instrument itself, because you can start playing around with the measurement situation, see kind of how thick do my layers get just at some high concentration, just to see it. Compare that to actually, if you take the dimension of the molecule and the density of the molecule, there you have all information to actually calculate a frequency response. So, but just that the molecule, the length of an amino acid, for instance, can be around 3-4 nanometers, and then you would see, okay, that would be some number of hertz, like 10 hertz, and then you can actually compare the measurement and see, did I get anywhere close to a monolayer of that, or am I getting a much larger signal that would signify multi-layers? So that's one thing I always do. I try to predict what amount of absorption should I expect with this molecule if I get a monolayer, and that's a good comparison number to have there. And then you can start playing around and take time, so you're sure what happens with the kinetics there.
I would say that's a good comment, to have good knowledge of your system, as you said, to know what kind of signals could I expect. That's a really good thing to keep in mind as well.
Yeah, great. So I think we will end this episode with this. So thank you, both of you, for sharing all this information.
Yeah, it's a pleasure.
And thanks to everyone listening. And I also would like to take the opportunity to mention to those of you who are listening or watching that if you're interested in surface science or related topics, you should also check out our blog, the Surface Science blog. Thank you.